right, guys, how's it going? Beautiful rainy morning in Istanbul today. I'll go ahead and get started. This talk, it's titled Introduction to ZK Security Research. There's a few other talks after this that go into like other specific things, and since this is only 16 minutes, I'm going to talk fast, and I'm going to kind of drill down on like a good introductory section for this. A little bit about me, I'll blow through this. I was an exploit dev for many years, and so my background is traditional security research, kind of like you guys, a lot of the people in this crowd, so it's kind of nice to talk to people from a similar background. Multi-year nomad, love mountain biking. I've been at the EF for like 2 years, mostly focusing on finding bugs in the client implementations, the EL and CLs. But yeah, it's kind of at night I look at ZK stuff, very interested, and spent about a month earlier in March at the ZeroXPark ZK residency, focusing on ZK security research. I'm also the Airstream guy. The decentralization of my chain allows me to work from Starlink inside of this little Airstream from wherever I want in the world. So that's all over the central and western United States, where I spend summers with my wife and our dogs, mountain biking in the day and finding bugs at night. Cool, so what is this talk specifically about? It's about bug classes seen through the eyes of a security researcher for security researchers. I'm not going to dive like deep into the proving systems and like the polynomial commitment scheme and other things. Follow me on Twitter for more information later. Infosecule is my handle. It's in the middle of this slide. We will be talking a little bit more about like the different cause layers of bugs, and we'll release some material later. But this one specifically focuses on circuit, and we've kind of identified application framework and the proving system like as other layers where this where we can see problems. If you want a little bit more depth, a longer form version of this talk that's like twice as long, like around 30 minutes, will be at Programmatic Crypto on Thursday at 2. I don't even want to try to pronounce the name of the stage because I'll definitely blotch it. Yeah, if anybody wants this QR code, there's a 1-hour workshop that was in Vietnam with a bunch of people a lot smarter than I am working in ZK, kind of discussing all of these things, and it's a lot more in depth, and it's kind of where this presentation originally was formed. Cool, so I'm going to talk a little bit more about circuits mostly, and so I want to talk about specifically like the types of bugs that we see in circuits, and introduce like a terminology that we can kind of use to classify these. So the categories are here, and I'll go through each one kind of individually, and then talk a little bit about other stuff at the end. So the first one is like general logic missing constraint, and I don't want to spend like too much time diving into the example, but I do want to kind of highlight one thing at the beginning, and it's this like conceptual view of what circuits look like. And so you have this prover that's proving something and there's a circuit involved, and then you have this verifier that's verifying something and there's a circuit involved. And a high-level way to think about this for like traditional security people is like server and client-side sanitization. So if you are preventing or sanitizing like for SQL injections or some type of overflow or something like that, server side, good job. If you're doing it client side and I just go in and view source and edit the JavaScript or something, then you have a problem. And so a lot of these bugs we've seen, all of the soundness bugs, are issues in the circuit that's on the verifier side, right? So you can think like server side. So in this particular case, there was no differentiation in this Merkle tree. And there's more information about this on the next slide. There's no differentiation between like the leaf nodes and like the leaf node depth and all the branch nodes. And so what you could potentially do here is make a proof where your prover is actually constrained to, they just assume that if you add something to the Merkle tree, you kind of do it in order. But the verifier actually didn't have a constraint on it. So you could add something somewhere else and like potentially brick the system. I think in this case, it was like allowed you to like have a second nullifier so you could double spend. It was in Plonky 2. There's a link at the bottom that has a lot more information on this. This actual example, I think, is also on the ZeroXPark ZK bug tracker, which I'll provide a link to at the end. It's a pretty good one. So this is by far the biggest one we see, this arithmetic underflow and overflows. So ZK often requires modular arithmetic over a scalar field. Since all of the operations are done mod p, we can experience overflows and underflows when the value of addition or multiplication exceeds p. And p is the order of the scalar field. So p is like this large prime number, and everything, it doesn't matter if you've got a string, an int, it doesn't matter what your data type is. If you're using it in these circuits, all these polynomial commitments happen to it, and there's all this other underlying stuff that I think from this circuit layer you don't really have to understand, but you need to think about from like your data type perspective. If you overflow this prime field, it just wraps around. It doesn't say anything to you. Sometimes we're okay with this, especially if we're generating randomness, but we're definitely not okay with this if it's like something like the index to a Merkle tree or something. So in this example, like this much smaller p, if you subtract 1 from it, guess what? You get the max. If you are from 1 from 0, if you add 1 to it, you get 0 again. Just a side note, if you're working with ZK EVMs or anything that's like Solidity-based, Tornado Cache, anything like that, BN254 is the only precompiled curve you can work with that's pairing friendly. So that really large number at the bottom is P in this case. That's a large prime number. Cool, so I don't know what's going on with the slide. I apologize about that. It's rendering a little bit weird. PSE ZK EVM SAR opcode, which is I think it's like shift arithmetic right in this particular case, was vulnerable to this. Basically, this happens, I think it's when the shift div can be greater than 4. So this particular circuit is vulnerable, and the fix is adding these 2 lines at the beginning just to make it like constrained to under 4. And if you go to this actual pull request right here, you can see logic where somebody like back calculated what the actual shift div needs to be in order to overflow this circuit. So you could potentially have 2 different proofs that would verify correctly, and one of them would put the rollup into like a stuck state, right? So potentially bricking funds or something like that. This is like a toy example to kind of understand this concept. So right here we have this lower statement says index mod p is equal to index plus p mod p. So in the top line here you see 9 modulo 5 is 4, but 9 plus 5 modulo 5 is also 4, but 9 does not equal 9 plus 5. Right? So this is really important because if you do these checks, like this false check right here would prevent things from happening. If you leave that part out, you have problems. And this is a really fun example. Aztec had a tree index bug where remember I talked about like server and client side. Client side, they were constraining this particular index that they were using for their nullifier to be a 32-bit number. And server side, right, verifier side, there was no constraint, right? So the problem here is that if somebody goes in and they fork the prover and they modify this one particular part and they allow themselves to have a 64 or 128-bit number, basically they could just add an F to the beginning of this, then they have the ability to have a second nullifier. And if anybody's familiar with how Tornado Cache works and most of these mixing pools, you basically have this like secret note that you generate, and you have 2 hash functions. And what you do when you make a proof to be able to do withdrawals is you prove that, so whenever you deposit, let me rewind, whenever you deposit, you hash the first hash on your secret, and you get this like deposit hash, right? And then whenever you're withdrawing, you prove with a ZK proof that you have a hash that's like the hash that you're presenting is the hash of a pre-image that is also one of the hashes pre-images from the previous hash list in the deposit list. And so whenever you withdraw, you post a second hash, and that second hash is also a nullifier, and that's what prevents you from withdrawing a second time. So it's the same, it should be the same hash every time you withdraw. But in this particular case, you could pass all of the hash constraints, but the problem would be that like your index into the tree would be different, so the nullifier would look different, so you could basically withdraw all of the funds that are inside of their privacy pool. And we saw a very similar one with Tornado Cache. Sorry, and this just is like a small view of exactly what I'm talking about here. You can see that no constraint on the index to keep it as a 32-bit number. This is like the toy example doesn't like, just for time reasons, doesn't like go into all of this, but like you can think about it this way, right? Cool. The less than chip, this kind of is interesting because this is also a mismatch type length, the previous example, and a lot of these kind of like run into each other. The mismatch type length for the ZK EVM's less than chip, it contains some constraints. Basically what the chip did was like, if I had a large number and I wanted to see like, is it less than or equal to, I just start with the largest byte and I compare those. And if they're the same, I keep going down the tree. And you can think about it conceptually like, if one byte is like, the largest byte is different, then you already know that it's bigger the other ones you don't have. So it's like for optimization reasons. The problem here is that it wasn't constraining each like check to the byte size. And what's even, just so that you can conceptually understand what's happening here, it's taking a byte each time and comparing them, but it's not taking a byte input. It's taking 8 1-bit inputs, these wires in the circuit. So this is like where our mental model as traditional security researchers kind of breaks. And this ended up being a problem. it was actually stated in the chip, and you can see for time reasons, I'm going to blow through this. It says right here under this like pub LT column advice, denotes the byte representation of the difference between left hand and the right hand side. Note that the range of each byte is not checked by this config. Of course, this was actually used somewhere where somebody did not constrain that, so that's a problem, right? So this allowed a malicious prover to generate random proofs that would pass the verifier that could brick the rollup or steal funds, or who knows what the possibility is. But at minimum, you could brick the rollup, which would be a huge problem. So this is a good example of like, this happens all the time. Let's say that I have memcopy, or like I have printf versus sprintf. If my function states undefined behavior if you don't give a length, like people are still going to make mistakes. So we've learned these things over the years with memory unsafe languages and other types of things. Let's not make the same mistake like moving forward with ZK. So talk a little bit more about like how to prevent this later. Yeah, for time reasons, I'm actually going to skip through this one. This is just another opcode. And I apologize, it looks like the way that the PowerPoint rendered is kind of odd. I will tweet a link to this, to the PowerPoint slides after this. Cool. Another, assign but not constrain. This is kind of the difference between the client and server-side sanitization model I mentioned. The previous example is a good example of it. I said these overlap, right? A really famous one is this memc hash. So this outs array, the first byte of the outs array was basically the single equals in CIRCOM. And this is like a huge common mistake in CIRCOM. I think last year at TrustX, Barry got up and was like, if you don't see like the double equals arrow and it's just a single equals, then like you probably have a problem there. And what that really means under the hood is that your client side, right, the prover side, you're constraining something, but the verifier you're not. So you're leaving it wide open. In this particular case, it basically made it where you could make multiple hashes. You could like modify the hash on the same deposit note, which would allow you to potentially withdraw a bunch of funds. Tornado Cash actually, I think, saw the fix, was live for 6 months in a PR in the repo, and went and drained the entire Tornado Cache and redeployed before any hackers got to it. So we got really freaking lucky with this one. Cool. Non-deterministic circuits. This is kind of an interesting like mental model as well. I'll explain in a second. Basically, there's different ways to create a valid proof for a certain outcome. Good examples of this is the memc hash, Aztec tree index, and what you can think of is like there's actually no input and output in a circuit. There's like this Boolean yes or no for the verifier. There is technically like inputs into the circuit, like the data you're putting in, but there's no like directional thing. It's a system of nonlinear equations. So like on both sides of the equals, it's not like traditional programming where you're like setting a variable to something. If you have this double equals in CIRCOM, or if you have a constraint in Halo 2 or these other proving systems, or frameworks I should say, then it's kind of like the variable is 5, but 5 is also the variable, and it's like it's a weird way to think about it. So the problem here is that you can basically have like different answers to the same question and still get it true. And the Aztec Peterson hash input, for time reasons, I got like 3 minutes left. I'm not going to go into it. Basically, you had multiple hashes for each data input type. So if nullifiers are being used, that means double spins, right? And every time you have stealth addresses, you're using these types of things. Cool. Compiler optimizations. This is a fun one. So this is public key, private key, like signing. Like you can think ECDSA, but using ZK. In this particular case, you have 3 inputs. 2 are public, 1's private. The private key is a private input, right? This is something that like you can think of like the witness in ZK. So it's not going to be public. But in this particular case, you sign a message, right? The problem with this is that even though we have this public message, there's no constraints on M. The variable M is not used anywhere. So what ends up happening here is there's actually no constraints made. CIRCOM, the compiler, will not put constraints on this, so that allows replay of messages. So I could change M and steal the same signature of some other M you've signed, and it looks like you've signed it. What's the fix? This really odd thing right here where you square M to make a dummy variable that just creates some random nonlinear constraint. I don't actually think this is totally secure because like this will add entropy to the output of the circuit whenever you do fiat shamir, but this will, until somebody solves how to break that, like what you would probably want to do is get a ZK-friendly hash function and hash M with the public key or something like that to kind of like cryptographically root it in. Cool. Halo 2 had a bunch of problems with this too, but they're different. In Halo 2, you actually don't use the triple equals. Whereas in CircCom, you basically write the prover and the verifier circuit at the same time, depending on how you denote things. In Halo 2, you have these instance, fixed, and advice columns. There's this particular column, like a lookup table. So like, let's say that I'm shawing or whatever, doing a CRC, some checksum on every opcode in the EVM. Well, there's only 160 something of them, so why would I compute them each time? I would just pre-compute them and make a lookup table and make it much faster to look them up. So some of these lookup tables, that would be like an example of a fixed lookup table in a circuit. But there are some that are dynamic, so there's a lookup table, but it's based on, there's like smaller equations, they're based on some variable. In this particular case, the floor planner, which is something that Halo 2 uses to optimize and like reposition circuits physically after you're done like actually writing the constraints, it will optimize out these things. And so you need to like tag these rows where you actually have like empty columns. And I am like completely out of time. I'm gonna blow through this Fiat Shamir stuff. Actually, I'm gonna skip it. This is a good example of Frozen Heart, if you wanna look it up, of like the proving system having an issue. Fiat Shamir, which basically makes us able to do non-interactive or interactive proofs to turn into non-interactive. There's an issue with the entropy here and rooting it. There's a bunch of other stuff that I'll talk about in the next talk at Prague Crypto on Thursday. Come check it out for possible solutions. Also, Ali's about to come up and talk a little bit about this stuff, especially the education for auditing materials and stuff. And just for like the disclaimer here, I want to say my thanks. Slides go for the template. I think I legally have to do that. Definitely the ZK security research team at the Xerox PARC residency, the ZK residency. The PSE ZK EVM team, I picked a lot on their circuits here, not because their circuits are not secure, but because they actually provided me a bunch of examples of all these things. So they were really great. And then Kyle at Xerox PARC. This GitHub right here is awesome. It has this bug tracker. They use the same terminology to start like classifying these circuits. If you're starting to look into ZK security research, this is a great place to start. And with that, I will hand it off. Thank you guys.